My name is Siddharth Panda, and I'm the coordinator of the National Center of Flexible Electronics here at IIT Kanpur. Greetings to you all on the occasion of the National Technology Day. On 11th of May 1998, India achieved a major technological breakthrough by successfully carrying out nuclear tests at Pokhran. In addition, on that day, the indigenous aircraft, Hansa 3, was test flown at Bangalore, and also India performed a successful test firing of the Trishul missile. Considering the above technological achievements on this particular date, the day of 11th May was chosen to be commemorated as the National Technology Day. The National Technology Day is celebrated every year in IIT Kanpur, and this year, the celebrations are being organized by the National Center of Flexible Electronics. The National Center of Flexible Electronics was established in 2014 with a grant from the Ministry of Electronics and Information Technology, Government of India, and with support from IIT Kanpur. The vision of the center is to catalyze the growth of the industry in this sector in the country. The center is engaged in developing several technologies with the industry and for the industry, which is the mandate of the center in this emerging area of flexible electronics. We have a company incubator at the center where not only the R&D, but also the manufacturing happens in the center. Flexible electronics has several advantages over conventional rigid silicon-based electronics and has the potential to provide solutions for several of India's unmet technological needs. The lecture, which you'll be hearing soon, and the demos outside will provide a glimpse of some of the possibilities of the technologies. Now, I invite the director of IIT Kanpur, Professor Abhay Karandikar, to the stage to address the gathering. Professor Karandikar.
Good afternoon, everyone. First of all, on behalf of IIT Kanpur, I would like to really welcome all the school children who have gathered here for celebrating this National Technology Day. As Professor Panda just pointed out that 11th May, every year we have been celebrating it as the National Technological Day in celebration of the technology breakthrough that our country achieved in the form of nuclear tests. And since then, we have been celebrating it every year. And it is quite appropriate and fitting that on this occasion, we celebrate some great technological advances that have taken place and that are likely to shape the future of the humankind. In this respect, I'm delighted to know that National Center for Flexible Electronics, which has been working at the forefront of what is called as flexible electronics, and I'm sure you would know that what is really meant by the electronics being flexible in the talk that my distinguished colleague, Professor Mahapatra, will be giving. So I don't want to talk about what do you mean by the electronics being flexible. And in his talk, I'm sure he will excite you with what are the possibilities that emerge with the new kind of materials that can be used for the electronic devices that will really make, many possibilities to emerge, which really would seem like a fiction, only a few years ago. As you know that IIT Kanpur is one of the premier technical institutes of the country, and we have a large number of departments working in several areas of science and technology. We have traditional areas like electrical engineering, computer science, and mechanical, and so on. but we have been also now active in an otherwise non-conventional engineering, like some, for example, biosciences and bioengineering, material science and engineering, and several other interdisciplinary programs that the Institute has been active. It is really difficult for us actually on a National Technological Day to showcase one technology because the entire institute is really involved in many activities that can be really showcased. But I'm sure with this today's lecture, you will get a glimpse of at least one of the technological advances that have taken place. I hope you will not only enjoy today's lecture, but also your visit to the Institute. We intend to sort of invite the school children many more times in the near future. We believe that today's school children could be the future students of IIT Kanpur, and we would really like to excite them so that the school children get motivated to come and study in IIT Kanpur. So with this, I welcome you all for this, and we will go ahead with our next program, and which is a lecture on the flexible electronics.
Hello. Hello, my young friends and my colleagues. This will switch. I really feel like back to school. I'm also wearing a white shirt. All your school shirts are white, is it? Okay. Switch. अरे इसमें नहीं, इसको बंद करिए. Oh God, desktop. Okay, so let him put the slides on. This lecture primarily is towards my young friends who are going to become technologists in future, and not for people who are already engineers and scientists. Okay, and hence I'll keep at that level. My aim would be to make sure that you understand at least what are the basic challenges of this new area, so that you can think of many applications as you grow up. All right, so it's yeah. It is on, no? Okay. Yeah. Okay. All right. So on a technology day, when a new technology comes, you must have heard DNA, right? DNA is what? Okay. So, and that leads to gene, okay, and that leads to evolution, right? So similarly, technology is really DNA of a society, right? And I have titled this, "What if?" My professor used to actually ask. If you say something, then it says, "What if?" Right? And then most technologies in the world has come out of this question. Okay? What if, when there was black and white TV, and you wouldn't have seen. We have seen a black and white TV also. And at that point of time, somebody thought, why should it be black and white? Okay, why can't we make it color? And there was a transition. So similarly, technology comes out of this asking a question and then dreaming, why is it not possible? and then somehow it happens. Okay? So, so you are familiar with electronics, right? You study electronics, class 10 and 11, correct? Diodes, transistors. No, you have not studied? Okay. So, in class 11 we do that, 11th and 12th. So, they have not studied but they have done resistors and all right. We will limit to that what we actually understand. The question is, why is this question important? First thing is, which means conventional electronics is not flexible. Okay? So, anything, your mobile, is that flexible? Or can you bend it? Can you stretch it? You can only break it. Right? Okay. So, this is an electronic, okay, that's in a box. So, most of the electronics is in a black box, right? And that's because of some limitations of the technology. Okay. So, now I will try to show you what effort and all worldwide is being done such that that limitation goes for some of the applications. And actually, this is going to not just evolution, this is going to go through a revolution. Okay? We are hearing the footsteps of a revolution coming, and that is what I want you to go back when you at the end. All right? Okay? So, I'll tell you, most of the time I only talk, right? Most of the other people do the work. So, let's go. So, we have in India, as Professor Panda said, in flexible electronics in worldwide there is a huge effort to develop this technology. In India, we are the only institute where you have a very focused about, so these are team leaders or faculty members, something like 12, 13 of them. They are team leaders like IPL captains, but they are not competing with each other. They are trying to cooperate with each other to produce this technology. And so I will not go through, so I am also here, some of us all are here, and with each of us there are a lot of people working, and that is actually at the center's greatest asset. About 120 people in all at the center, okay, trying to work with this. And this is of course not in the lab, this is in a cricket field. Okay, we also play as a team. Okay, so and the focus of the being in India, this is being done all over the world, but being in India, our focus is of course the Indian context. So I will not go through. So all these areas, healthcare, environment, energy, food processing, everywhere this technology can, as I will illustrate, can actually revolutionize the field. All right, and we have what at the center. This I will quickly go through because actually I am speaking on behalf of the center, and everything that I will show you has been done by these 100 people working behind us. All right. So we have components. I'll explain some of them, and we have the major thing in electronics is we have components, but those components have to be integrated into making into applications. All right. So we have been working not merely last year or 2 years before. This center has its beginning in year 2000. So we have been at it almost 18 years. First 5 to 6 faculty members with 10, 15 students, and now we have about 7, 8 faculty members, team leaders of 12, 13, and with 120 people. But it's a 18 years of journey where we are at the moment. So we can make almost all the components and integrate into memory. I'll show you solar modules, applications like anti-counterfeiting, okay, anti-thuggery, right, okay, healthcare devices, and lots of displays and smart packaging. Maybe I'll explain smart packaging a little later. You know, smartphones, everything is becoming smart. So packaging also has to become smart. This is one of our major areas. I'll come to that. So this brief introduction to the center, which he did it in words. In the next 60 minutes or so, I'll tell you why flexible, of course, and worldwide efforts, what kind of efforts are going along, okay, and give you a primer of the key problems. We are feeling, I will not do very complicated application, okay, simple conductor that you have studied, we will also do that, all right, and so we will do materials and inks, and it is flexible. Once it becomes flexible, we can print, right. So printing electronics, I'll do, and I'll summarize with current challenges. That's our task. Let's go. So diodes, S missing, okay. So you have seen them, components like this, diodes, transistors, but these are discrete, okay. And then if they get integrated, they become, what is it called? Integrated chip, IC, right? So can anybody tell me what a typical computer chip has, Pentium chip, has how many transistors in it? Have you studied? Has anybody told you so far? No, anybody? Any of the school? How many transistors in a typical Pentium chip? Pentium is a computer chip, right? How many you guess? How many transistors would be there? Okay, so there are millions. In fact, the recent chips have 2 billion. Okay, there is, Indian population is, okay, but in one chip, one computer chip has 2 billion transistors. Okay, so that is, so the power of electronics comes from this integration. Okay, that is conventional electronics. And you know, we used to call our age, sometimes humans lived in Stone Age, correct? And after that, which age came? After Stone Age? Iron Age. Okay, some people call the recent age also Steel Age, the amount of steel that we use. Okay, but what is our age? Can you name a material which will characterize our age? Stone? No. Brass? Steel? Okay, I'll hold something in my hand. Can you tell me what is this? Sorry? Brass? Glass? So somebody is saying, okay, so I think they deserve a chocolate. Okay, this is a 6-inch wafer of silicon, all right, and on which you would have many computer chips, like 1,000. Okay, this comes in 6,000, a 6-inch, 10-inch, 8-inch, even 12-inch now. And so all your computers are made on top of this, and then they're split and put into a computer. So that is why it can become so cheap. You can make thousands of, and each one containing how many transistors? Billions of transistors. So that is the power of conventional electronics. Except that, if I drop this, shall I? Okay, this will break into pieces, right? So, and this is a part of a single crystal. Have you studied crystals? Yes. So this is a single crystal which weighs hundreds of kilograms. One crystal, not many, okay, which is grown, and then you dice and cut and make wafers like this. Okay, so conventional electronics, everything that you see is made, your mobile chips, all are made with things like this. And so, so you have to require one single crystal of silicon, this is the material, okay, and from that everything is made. To be able to make that silicon, you have to go to very high temperature, that is the melting temperature of silicon, to produce one crystal, and then lots of other things are done. Okay, so it requires, first thing is, it requires, is brittle, and it requires very high temperature, all right, and hence I cannot flex. Okay, I feel like breaking it. Okay, I'll not. Okay, so so that has to change. So you can go to nano, okay, but for any electronics you require these two components. Of course, you require resistors, capacitors, but you require diode, which we call the wheel of electronics. It has 2 legs, right? Okay, once you have a diode, it has some intelligence in the sense, in one way it can conduct, in the other way it cannot, right? So in a conductor, it conducts both ways, right? And if you have 3 legs, you can do a lot more things. Okay, all the controls come really because of transistors, and you put them together, and then you get all kinds of electronics. So if I have to do flexible electronics, which means I have to get diodes, every component in a flexible form, and not on silicon, okay, which requires extremely high temperature, and is brittle, all right? So that is the challenge, okay? So what happened? So can you locate silicon in this? You remember this, right? You have seen this. Where is silicon in this? Okay, silicon group 4 here, right? So our age is called silicon age because information, electronics, all computers are all controlled by, at the moment, silicon. So you can call it silicon age. Some people call it information age, and soon we are going to call it AI age. Artificial intelligence. Everything is artificial intelligence. So the mobiles need not be only smart. They have to be also artificially intelligent, right? They can do translation now, right? Google phones now can do translation as you speak. As I speak, it can be translating it to Hindi, I believe. Okay, I have not used one so far. Okay, so but this electronics has some of the problems that I told you. So the alternative that is emerging for last few decades we are working at in the labs is based on, okay, carbon. Okay, so carbon is also in the same group. All right. So carbon based electronics of various kinds are coming up. All right. So can you tell me what is common to all these? Carbon, of course. Right. Okay. Do you recognize what is at the center? Buck-Bits, right. See, 60 carbon atoms. This is graphite, or it has become a single layer is called now graphene. A lot of research is going on. But what is common to, what is here? This graphite, this is diamond. You know sp2, sp3 bonding, right? You would have studied in class 9 also, bonding? No? Class 11, okay. All right. I'm forgetting which class you study all this. All right. But why have I kept this here? What is carbon here? This is organic. All right. This is not inorganic, but it's organic. We are also, every organic molecules are also carbon, hydrogen, and oxygen. So can we make electronics out of that? Okay. And then organic cannot go to that temperature. Silicon can be melted, okay. But organic is organic molecules which can happen at very, very low temperature. So that is a possibility. So this is, so all our lectures to start with some Guru Vandana, right? So I should start with a little bit of this area of Guru Vandana, right? So this was, these three people got Nobel Prize in chemistry for 2000 for the work they actually did in 1970s, okay? This is a Japanese chemist, Hideki Shirakawa, and he is a polymer scientist. So he was making polymers in the lab, okay? And McDermott is also a chemist, an American chemist, okay, actually New Zealander, but he was visiting Hideki Shirakawa's lab, and he was making some polymers. Then suddenly he saw these polymers are shiny, okay? Then he says, why is polymers are shiny? Plastics is not shiny, right? In your mirror, what is shiny? The glass is not shiny. So behind the mirror, what is there? Silver, the metal. So metal is shiny. So McDermott immediately understood that Shirakawa has made some polymer which has metallic properties. So polymers are typically plastic, but he has made, and he didn't really understand. But he was also a theorist. He immediately got interested, and a physicist, an experimental physicist, and a theorist together, okay, Alan Higger, got interested in the problem, and they solved and they showed that plastic can also be conducting and has electronic properties. Okay, this was in, so got Nobel Prize in 2000, and they are chemistry prize, but they are both physics and, right? The same year, we are giving prizes to Alferov, Kromer, and this man. Anybody recognizes this man? These two people got half the prize, and these people he got half the prize. And he was not working in any university. It was Texas Instruments. Okay? He was in Texas Instruments, okay? An engineer, electrical engineer. He is getting a Nobel Prize in physics. So discipline doesn't matter. Right? Absolutely doesn't matter. Okay? So does anybody recognize this person in the photograph? School people? No, you don't. Who invented ICs? The integration that I told you, this is called Jack Kilby. He is the first one who showed the power of integration in Texas Instruments. And he was, and why is, he is given much later. This work was done much earlier. Why? Because this was seen that ICs change lifestyles. They change civilization, okay, civilizational change. And any invention that changes society, that changes the way we live, okay, needs a Nobel Prize. All right, so why am I saying all this? This was also around the time when we started our center. Okay, 2000 Samtel Center, we started 18 years journey. All right, so taking ideas from that plastic can be made conducting. All right, and not metal. We don't need metal. We don't require a semiconductor, but plastics can be made conducting. And these people had shown that if you put two different materials, they're called heterostructures. Okay, you have if I put silicon on silicon by some method, then it's not a heterostructure, is a homostructure. Okay, but if I made some other material, gallium arsenide, okay, on something else, then it's called a heterostructure. And all our video devices and all that are actually made by the principles that these two gentlemen got. All right, and so these two gentlemen here use these principles of inorganic electronics, which we have learned for many, many decades, and produced an organic, using organic molecules, okay, a light emitting diode. Okay, that means using plastic, using the ideas of that plastic can be made conducting and hence electronic properties. Okay, so Ching Tang, and he was not in a lab. Now he's in a university, but at that time he was working for Kodak. Okay, and he was actually trying to discover solar cell, but instead discovered light emitting diode, which could be done with organic molecule, not with any inorganic semiconductor. Okay, and Richard Friend, now it's Sir Richard Friend. For his work, he has been now knighted by the British Empire. And Richard, he showed it for polymer, that you can make a diode, not just a conductor, but you can make a diode which is also luminescent, okay, with using a polymer. And both of them are extremely good scientists. They publish at the highest level journals. At the same time, they actually have companies to work with, or they actually make companies. That's the new nature of science and technology. Okay, the people who are working for principles also have industries going. So these two people did seminal work to get this field going. That is, you can make plastic all the electronic properties that you require. Once you can make plastic, then you can put them on plastic. You don't require to go to, okay, and if it is in plastic, you can bend it. Okay, so that is the key to flexible electronics. That low temperature organic molecules, okay, and all the processing can be done, and yet the properties are like diodes and transistors on flexible plastic. And then it is now extended to, as I will show you, not just any cloth, paper. Okay, so you can now make electronics on any substrate, okay, which is which can be also be bendable, and that brings in a revolution of sorts. All right. So you had inorganic electronics. This is all made at our center. Okay, so this is today's lightings. Most of these are not, but most of the lighting that you will see, these lights are probably, okay, are actually inorganic diodes. White light, the torches these days, right, are no longer these bulbs. These are light emitting diodes. They are gallium nitride based. Okay, even not silicon. Okay, so this is a nitride based, and we have an LED which is like a display. Okay, and we have solar cells. Solar cells, there are silicon solar cells working in space. Transistors, sensor and sensors, sensing of any light, chemicals, everything. So for one-to-one correspondence, okay, whatever is there in electronic, there is an effort to do that, but not to replace silicon. In fact, there is a theorem almost for us that what silicon can do, don't try by any other method. Okay, so it's what silicon can't do, you do it. What silicon cannot do, cannot make a display like this, right? But since my plastic can become an LED, I can coat plastic at very low temperature and make a huge big display, which silicon or gallium arsenide cannot do. Okay? With a silicon, I cannot make a electronic circuits which I can wear, okay, like a jacket. Okay? But with if all the electronics is plastic, I can wear it, right? And it can be extremely cheap. To make a crystal like that, okay, you require $1 billion factory. Okay? To make this is very cheap. Okay? You can do it in the lab, and hence, okay, many things, and that is what is it that I'm saying, not only flexible or bendable, but also large area. Large area at low temperature if you want to get, and then if you do large area, then the cost is also low. Okay? So is large area cost effective electronics that you are looking for. So typical components, why is it very simple? You don't have to worry about if you don't understand, but it is, take a, let's say plastic, instead of glass or plastic, and just simply put one layer and the other layer and third layer and make a device. It's not like a huge factory that you would require. I will not press on this at the moment. There is nothing at the moment, none of the products still which you can go to the market and buy. Okay? But there is a huge effort to produce many, many new applications. And which means we are just at the right edge of this technology, that it has not hit the market, but many people are trying to. So just an example of what people are trying. Okay? So let's say you have a packet in which there are fruits, and this is a label which will figure out whether the fruit is fresh or not. So electronically you can figure out, okay, or if because of the gases that are coming out, okay, you can figure, or milk, the milk has gone bad or not, right? So this is called a smart tag, okay, or a smart packaging. Okay, so these are, so, and this has to be very cheap. The cost of the fruit small basket, okay, so this has to be few paisa to be able to be useful for that. So you can't have a big electronics put there. Electronics can do it, but that is not, okay. So similarly, OPB, I will show you displays. You can see displays which can be bent. In fact, already in the market there are things which you can bend. This is the most interesting. A Japanese scientist is actually, suppose a robot. A robot has to have skin. Okay, so what will be that? The electronics which has diodes and transistors and sensors which will be there, and that will be like the robot skin. Okay, so if we can do many, many kinds of transistors put on plastic and make artificial skin, so that when you are handshaking with the robot also knows what pressure you are giving, right? Or who are you? Okay, because of the sensation, and the sensation must be through this electronic components that are on the skin. All right. So ID, some of you are using badges, but now in our institute also ID. So these ID are dependent on RFID. Have you heard of RFID? No. Okay. So the ID tags we can make it cheap. So there are many such applications people are trying, but none of them so far has become commercial to the extent you can go to Kalyanpur and buy it, right? But that is the success of technology, would be some of these things when hit Kalyanpur market and you can go and buy it. Okay? In fact, it happened to white light LED. Okay? When it hit the Kalyanpur market, they got the Nobel Prize. Okay? They got Nobel Prize. They have been working for all their life. 3 Japanese scientists have been working all their life, but they had to wait to get the Nobel Prize when it changes life. It saves energy and changes life. All right? So this is going to do that. There are, in medicine, for example, a diagnostic patch. Okay, if it is plastic and can do electronics, it can do a diagnostic patch. Okay, and or a full laboratory on a chip. Okay, which there are experts here, but I'm just saying that there are many applications are coming up because it's cheap, it's large area, it can be done on plastic, and it can be done in many different ways. In fact, we we all keep on saying that this area is currently limited by your imagination of what kind of application you want to put to. Okay? But it has to become viable and it has to become a proper technology. So that technology development work I will like to illustrate. So to summarize a little bit, this is the conventional electronics was microelectronics, okay, or I was almost going to a nano electronics. This electronics that we're talking about is macroelectronics. Okay? In fact, sometimes we say it is meter electronics. Okay? That is, you can go to a shop and tell me, 2 meter ka TV dena. Right? So it is like a than, right? Okay? I mean, I'm dramatizing it, but that's the kind of technology that we're talking about. That devices don't come in boxes, they come in rolls. Okay? And they can be cut to give it to you. Okay? And they're so cheap, you use it as long as you want. You want on a picnic, see the TV and throw it out. Right? You don't require it anymore. So it's disposable. So the kinds of, all these components are electronics components, but they must be printable. Okay? I can't make devices one by one if it is not. So it has to be printable in a very large scale. It must be flexible so that I can roll up, put in my bag. Okay? It has to be large area, it has to be disposable, and of course if it's disposable and all that, then it has to be very cheap. Okay? If it is very costly, then I won't dispose it. Okay? Or I would not make it that way. So these are the attributes that were, and we are talking about meter electronics or macro electronics that were, okay, this can be done by two methods, as I told you. One is small molecule. Small molecule, have you heard of benzene ring? Yes, okay. So now chemists are magicians. As a physicist, I think I have a lot of chemists working with me. Okay, they're like magicians. They take a benzene ring and attach lots of benzene rings and attach other whatever they want. Okay, and that becomes a small molecule. Okay, many of them, and they have the right properties for the kind of applications that we're talking about. However, small molecules require vacuum and they get evaporated and we can make devices. But then it will be small, right? This cannot be made in a large area or a stuffed large area. There is one company in Germany who has been trying that even on a very large area. Okay? So that is, but people are trying. This is also plastic electronics. Or you can do it in the lab like mix, solution, and chemists are magicians. They just do this and something new molecule comes out. Okay? In the conventional electronics, we are limited by silicon, gallium arsenide. In this electronics, we are not limited by, okay? Every day a new molecule is invented, okay? Which can be, so they keep guessing what will be useful to us, physicists and engineers, okay? And chemists keep trying new molecules producing. And there are hundreds of them, thousands of them to choose from, not limited by one element, silicon, this element or that element, all right? So, so this is a simple process, that is solution processing. So either you can do by evaporation or by solution processing. But I'm talking about macroelectronics, but these actually properties are controlled at a very, very molecular level. So this is done nano engineering. In fact, we embed buckyballs into our devices to control their properties. Inorganic, but nanoparticles are embedded into the, okay, or we align them or blend them. So nano engineering is required even to control properties which are in meters. All right? Just to give you, let's go to the first example that I want to give you. The first thing is, if I want a circuit to be made, then the circuit has to be connected, right? So how do I get on plastic metal? Okay? So that is, I require, so I have to print or I have to do something. So I require conductive inks. Your normal pen ink is conductive? No. All right? So we require conductive inks to do that. And so we have a group here, all kinds of inks, but I'll demonstrate to you today some conductive inks that is done on plastic. All right? So this is the conductive ink group, all of them are here. You will, while going out, you will see many more demonstrations. But I'll just tell you the basic principle. Okay? So we actually make all kinds of, first we do what is called a nano ink, and of semiconductors, of many different things. I will not explain to you that, but so it's actually ink, polymer, gold. Gold when in very nano form, 2 nanometers or 3 nanometers, actually in a solution looks like this black. Okay? Silver, some dielectric ink, this is carbon nanotube ink, we can in the lab make such inks and then put it on, for example, here you can see gold on plastic for TFT. This has been, diode has been made. This is gold on the plastic. Well, I'll come to this for interconnects. So first challenge is to how can I make interconnects on a plastic. In silicon, what they do is put inside a vacuum chamber and then evaporate. It melts, gold melts and then evaporates and then makes an interconnect. Okay? But here, a plastic sheet, what temperature can it withstand? Maximum 160, 170. That is also very specialized. Otherwise, it will buckle. Right? So, how do I put gold or copper or silver on plastic? That is a challenge. I'll quickly show you what we do. So melting point of gold is 1064 degrees Celsius. Okay? But if we make it very, very small, 1 to 2 nanometers, there are many, many gold atoms. Okay? It is not really melting point, but I can, the sintering temperature can be brought down how much? From 1064 to 153. In fact, if you let them, if you have silver, which is in nano form, because there are many more atoms at the surface. And if the atoms at the surface, then they are extremely active, okay, than the bulk. And hence, they would not like to remain nano form. If you have it in silver particles in normal oxygen, it will actually burn. Okay? It will catch fire. Okay? So, how do I then handle that? So, but temperature can be brought down by making it nano. So, what we do is, okay, let us say 1 to 2 nanometers of gold, okay, 2 to 3 nanometers of gold we can make in the lab, and then my chemist friends can attach organic molecules to it. Okay? Then it doesn't, it can't, okay, so it can't come together. So, they remain suspended and remain nano, all right. And then when I want it, I give some heat, okay, so that they start vibrating. These things like tail attached to the gold start vibrating and then go away, and they can join up to make, and then this joining up is working at a very, very low temperature. Okay? So, and I don't know if you know that if it is a sulfur atom, okay, if it is any molecule with a sulfur atom, this has a very large attraction with gold. Okay? Thiol, have you heard of it? No. Okay. So, but we can do that. Chemists know this, these tricks. So, now let us go and see what, so this is the gold ink, okay, and then once it is heated, it becomes actual gold. This is the black ink, okay, which is what, why is it looking black? Because there are nanoparticles but coated with organic molecules, okay, but they remain nano. And once I put them on there and then heat it, when the organic molecules go out, they become gold. Let us look at it in a in a video. This where is the video? निकल रहा है, कहाँ है? बाहर क्यों निकल रहा है? हाँ, ओके, वीडियो कम निकल रहा है. Okay. All right. But why is video not working? Huh? Yeah, also, yeah, but I didn't want to do that, so okay. I didn't want to do that. Okay, okay. I thought it was embedded properly. I tested it out, but okay. So okay. So you can see it is this is now heating up. This is the temperature shown here, 140. This is still black. You can see this black slowly turning to Okay, so if you can run it again. Okay, so it is now perfect gold. So it's come down to about 140. So it is black, and then I was monitoring the temperature while I was heating it. So it started around 145, and by 153 it has become totally gold, right? So in fact it's actually at 145 degree, except that the temperature is not uniform, and hence by 153 it's absolutely okay. So let's go back to. So that is one way of getting that. So using that, we also have pens, okay, which can, like normal pens, okay. We have made silver ink, which doesn't even require any heating, okay. So these look like normal pens, but they have been filled with ink which has silver nanoparticles with that, okay. And hence, when I write, I actually make conductive pattern. All right. So let's look at one such. So these are paper. This is some glossy paper, okay, on which we just write with this pen. It can make circuits. Okay. Wouldn't it be nice to make yourself? You can actually make whole circuits. Otherwise, how do you do it? Normally, you have to give a drawing to a PCB, somebody who makes a printed circuit board. It will be etched and it will be on a hard board. Here, if you have this pen, okay, you can simply draw your circuit and mount components. All right. So let's. Okay. So this is some dots are there. So I have one component. Okay. Okay, let me just, so first all right. So I don't know if you can see it is glowing at the moment. This is what I have drawn with the pen. So this is a battery connected here, all right, and this was not connected, and I've just connected and it is glowing. I think this is saturated. Okay, this LED I can switch it off, and yeah, okay. So this is simple. We can even do this by connecting it right here. So these are, I put it here, they are not connected. I put it, this one is on. This one is on because it's connected to the battery. But now, if I connect, this is my pen. I am not doing it very neatly, but you can connect it, and that is that easy. ओके नहीं है ना या तो बच के करें all right, so it's now glowing. Okay, so we have several such pens of different kinds. Okay, so I'm just showing by one line, but actually you can make many things. Some of them you will see actually outside also. All right. Now that I am here, how about this? This was on paper, okay, but we took a cloth like this. It's like magic, right? This is black cloth, and then printed our similar ink, not same, similar ink on it. Okay, this is cloth. Okay, so now if I connect an LED, okay, on this cloth, you think I can make a connection between the two? This is simply black cloth. This is just to prove that black cloth is not conducting, right? That I am sure you will know. But now I take this cloth, Okay, and now connect one end to my hands are slipping. इसको connect कीजिए थोड़ा slip मेरा hand से connect कीजिए जल्दी जोर लगाइए स्लिप हो रहा है ना हाँ okay and this end okay so this is okay so this is actually cloth which you can wear okay what use is this is flexible as it can be right and this is only in fact between this diagonal itself is about only 1 ohm centimeter. It's extremely conducting. You can see that, right? What use is this? It has tremendous uses because this can prevent electromagnetic. I'll show you. Okay, so you will see some of these. Change kar dijiye. Change quick. Okay. All right. There will be many more. Some of these, and this is non-toxic. This is water. This ink is water. Okay, and hence is eco-friendly, and it is no heating was required. Gold, I required heat, right? But silver, I didn't even require heat. I just had to dry it, writing. Okay, and it is of course low cost. And soon probably in your school will give you kits to work with them, okay, as a hobby kit. All right. All right. So I showed you this, the conductive cloth. So one of the application, in fact, one of the manufacturers is working with us to have your cards, okay, covered with that, so that nobody can actually steal the information. Because these days with remote you can steal your ID. Right. So if your wallet has such a cloth, you can't do that. Your passport, which is now electronically, okay, or wherever you want to do a very precise experiment in the lab where you don't want any signal from outside to interfere with the experiment. Call for our cloth, all right, okay, and cover it up. So actually the amount of uses this has, okay, is so large that we think. It should be, there are people in the world also trying that, but nobody still has hit the market as such. Let me go to the next application, okay, which is what I started with, and that is organic light emitting diode, right. So light emitting diode, which was inorganic, could be made on, right. So this, let me, or we have a group which pointer kahan? Yeah, right. Okay. So you know lighting, right? You know all this. You can see that efficiency of this lighting, but there are lots of other things. Okay. But one of the main thing is it has a point source, either a bar or a like this. Suppose I have large area organic light emitting diodes. Okay, then I can paste it anywhere in architecturally, okay, and then the roof could be actually covered completely. So the light would be not intense at one point, but nicely distributed. Not only that, just like fan meter, okay, you could actually change the color. Okay, you would have a color change, or maybe with AI, it will sense your mood and change the color according to you. If you are in a depressive mood, the artificial intelligence can sense your depressive mood and make the room brighter, okay, and lift your mood, okay. So all that is possible because it is large area, and now it has become even architect's delight, okay, to be able to integrate it into the architecture. So this, let me see how it is made. A little bit of, okay, it is very simple. That is the substrate. Substrate could be plastic or glass, and that is what you are trying substrate. On that there is an anode. So any electronic device has an anode and a cathode, and in between several layers, except that these layers are very carefully controlled by the machine to have only hundreds of nanometers of a particular material. Okay? And this is the heterostructure that I told you. Different kinds, that was actually a breakthrough. The breakthrough was that you don't try only one kind of material, but several kind of material in a series, and this was heterostructure. This is what we learned from inorganic semiconductor. All right? And that worked after many, many years. Okay? So what you do once you you connect it, and then the hole goes, an electron goes into that material, and that recombines to give you light. As simple a, okay? It is simple principle, but making it is not that simple. Okay, as my OLED team would tell you, okay, but I will show you some. So this is simple OLED. This is not like gallium arsenide technology, getting into a big factory and then making these small LEDs. Okay, it can be made over large area, and so let's see how it is made. So one way it is made is actually the vacuum technology. We have just 50 meters from here, we have a machine which has, this is a robot, central robot, all right, and these several layers of these materials are actually for, there are three kinds of, for white light, okay, you require three complementary colors. Okay, for example, in your TV, for example, the color is controlled by three colors, right? Green, blue, and red. That's correct. So what we also put is materials corresponding to which will give you that light coming out when electron and hole recombines, that green, blue, and red, so that you can get white, or you can just get green, you can just get red, and you can, okay, so we can do all that. So what we do here is you can actually put you put your substrate into this. I'll show you through a video, okay, and then it goes in, and then there are three of them, so three different layers. A metal, one metal we already prepare and put it in, and then we deposit three layers and a metal, and it comes out. It's as simple as that, okay, except that it is done in a highly controlled fashion by this robot with the three different. So you can see there is the metal chamber, organic chamber 1, organic chamber 2, and then there's a cleaning chamber and this glob box. This is the glob box. All right. So you put it in and you actually get it back here in a finished form, and we'll show you that. Okay. Finally, I have to get back to the video. Let's see the video being made. This is okay. So this is actually going, almost going to the lab. This is just nearby, next to this building. All right. So this is the you can see this is one of the chambers. Okay. So he is putting the substrates there so that he can handle it. So this is the substrate. Okay, so he is handling it in the glove box. You can see he is wearing the glove. He is not touching it directly. So this is that glove box. He put it in and it went in. All right. Then he comes. It is completely controlled by the computer after that. All right. So this this will take it to the right chamber. This is at this. The vacuum is changing here. You can see that, and it has taken to the chamber, deposited there, and get to the next chamber, and the next layer is deposited. Okay, and so you can see that it is going to the next chamber, and then after it has gone to that chamber, he just deposits that material. This material is getting hot and is evaporating, right? So the next layer, and it has to be only less than 100 nanometers of exact thickness. Okay, and then three such layers, and it comes out. And now we are applying current to this, okay, OLED. I can see this white. So as the current is increasing, okay, it is becoming whiter and whiter. It has become totally white light. So you can make tiles of these, or if it is flexible, on this has been shown on both on plastic and on. All right. So just to show you. Okay, so you can do this. These are not our examples, but this is LG's architectural panels. You can see, you can make. Okay, or this is the Audi office lighting, or this is the kind of lighting that you have. This is very much and in fact, you can have very, so lighting is, and you know how much is lighting cost of a building typically, lighting in terms of energy? 30% of energy that a building consumes, okay, is roughly lighting. And these are extremely efficient because there is no heat, okay. And so I will not go into that. So we have also produced some flexible, what I showed you is tiles, but this is done with rigid glass, or it can be done with flexible. You can see it, okay. This is currently under development, but that is, we have, so rigid glass, I do not know, you can see that it's like a very nice diode, very low current in one direction, very high current in the other direction. So this is like a diode, and this is the direction in which light glows, all right. So it can be done, and we have also done, our printing team is here, 7-segment display. All these clocks, we don't have one, that is the one clock there, but that is a 7-segment display of conventional electronics, all right. Now that's a big box, that watch behind, okay. It has 7-segment display. All your LCD watches also 7-segment displays. So that we have done on flexible, okay. And some manufacturers want it for very equipment like weighing machines or even petrol pumps, which we have already shown. This is of course one color, okay, but it can be done in many different colors, all right. We have a dot matrix display. There is a 7-segment only, but in dot matrix you can have even characters, all right. So we have also made dot matrix displays with this, okay. This can be also in multiple colors. I'll just run through them, some of the applications that we have done. So this can be actually, these are developed at the center. These are OLEDs developed at the center, okay, but this is vacuum evaporated. And so people are already Osram as doing signages, and Hella's automobile signages. This is becoming slowly getting into the market already, especially high-end automotive market. It has already created, all right. This is a project which we actually are initially we did of I don't know if you can recognize this actress. Okay, this is Wahida Rahman. Okay, one of our people mentoring us had actually Professor K.R. Sarma has was okay. And so this is a display that we developed fully under one project. This is a little earlier project. It is a passive matrix display that are developed, and idea is finally you would have actually displays which are flexible like that, all right. So OLED display, this is about 1.5 inch, okay, but this is not this passive matrix. There is no transistor at the back. Let me come to printing. So all this I have shown you that it is done by evaporation, but the real power of this technology will come if you can print on large area, okay. So print, what is printed? For example, newspaper is printed, okay, and it is printed for how many copies per day? Because the rate at which it's printed, okay, and so every day you have new newspaper for so many people in so many millions of copies, all right. That's because what is called the throughput, at what rate you can actually print them, okay. So now if electronics can be printed at that rate, it will be really cheap, and since it's in plastic, it can be not on plastic, you can do it on paper, you can do plastic, and I've shown probably on textile and cloth, okay. So let's see printing. So the real power of this technology that I'm talking about so far, okay, comes from the fact that it can be printed. These are marriage of two different things. One is which actually changed human society, okay. This was in 18th century Gutenberg's printing press, and this is a real conventional electronics. So if you marry these two and you print electronics, okay, there are two revolutions, okay. Obviously that the third one will also be a revolution, right, okay. So so the key thing is that it has to be large area processing, okay. It is not small area 6-inch wafer, it has to be extremely large, and it has to be fast, okay, the way the cloth is made, okay, at the same time. So that has to be done. So I hope this will also, okay. So let's show, this is taking a little bit of time, but we'll do this, okay. So let's see printing of being done in our lab here, just next to Okay, so this is a screen printer. We have all kinds of printers. Okay, we'll show you later. So this is a screen printing of a circuit being done. So this it now deposits a layer of conductive silver, okay, on top, and now it presses it through. Then again for a good thickness, it again puts it. So 2 layers. So the way it so just like you print banyans, okay, you can print circuits. All right. So is collecting, and this large area, this A4 sheet. Okay, so this is sheet to sheet printing, right? And you dry it for 2 minutes, and the silver tracks become conducting. All right. So you can now make complicated circuits just like by screen printing this way. All right. So let me get back to. All right. So so large area printing has become really industrial. This has the capability of making it industrial. And what I showed you is a sheet to sheet. But what we want to do is roll to roll. That is, you mount a roll, okay, and then it goes through printing and comes out with a roll, and then it is sent for applications. All right. So that is the real, and I'll show you. Okay. So we have at our center all these different kinds of printers. Okay, because we do not know for which application which one will be the best. So we have all kinds of printers. For example, even this is like your normal inkjet printer. You have the inkjet printer, except that we print materials here, metals, semiconductors. Okay, so we can do inkjet printing. We can do all kinds of printing. I will not go in. This is also another big inkjet printer in the lab we have, but this can handle much larger. So this is S2S. You'll remember. Okay, what is S2S? Sheet to sheet printing. All right, and what is R2R? Roll to roll. Okay, so you'll remember these 2 words, right? So these 2 different kinds of printing. So this is a printer roll to roll now. This is length is about 20 meters. This is not as yet we have in the lab. This is being made for us according to our design in UK, and it will be here in July. All right, so that we can actually okay. Okay. All right. So this is R2R process. You can see that what happens. R2R cleaning, printing, drying. Then we can do sintering. This is for making a heater. Okay, and you can see the way it is going. All right, and then finally it is drying, and then finally you have got something which is called a plastic heater. Okay, you know why plastic heaters are important? Okay, unless like heater, it can be inserted anywhere. For example, in your seat cover, okay, or inside your blanket. Okay, so there is a huge demand for heaters which can be inserted and are flexible. All right. Okay, so let's go to solar cells. Okay, so this is this. We have in IIT we have you have seen these solar cells, right? Okay, these are all hard. There are different kinds of technologies. Okay, quickly okay, so these are all amorphous silicon, multicrystalline silicon, and so on and so forth. But solar cells, the dream of Alan Higger in 2007 was that you actually make inks such that they can be printed. This was the dream in 2007. Okay, such that you actually print solar cells with the kind of inks that I talked about. Okay, on a plastic substrate, such that it can be ultimately printed like a newspaper. Solar cells, and here is one example like that. Right, this is a solar cell printed on. Okay, this. So we are soon we are going to print this. Okay, on a large scale and the roll-to-roll machine that I am showing you at our center. All right. So this is compared to. Okay, of course there are such things available. Right. Now you can imagine the kind of, this is not so flexible. Okay, it is flexible, but it has to be like this. This is also a thin film silicon solar cell. But that kind of silicon solar cells you can actually make in any shape you like, right? And you can put it on your bag to charge your mobile. You can you can carry on the go. A soldier can actually just make his shirt a solar cell, such that if he's in Ladakh, it actually gets power from his shirt, right? Okay, or tent. Okay, you just make a new tent with this, and you get your from the tent itself you get. So the kind of power it comes, the very fact that it is lightweight and is extremely lightweight. All right. So I am not doing very good with time. So this is we will start doing this also, but this is being done already abroad, like solar cells. You can see, you have heard of this experiment, right? A plane which goes only on solar cell, right? So, but this was not on, okay, this was silicon solar cells. Okay, how wonderful it would be if it is our organic solar cells, all right? Except they should last. So this is the solar cell that we make on paper, not even plastic, just on paper. Okay, so in our center, I'll show you. Okay, the flexible solar cell. I don't have time, but I'll still show you the solar cell that you make in another few minutes. Okay, so this is solar cell. Quickly. I'll take a few minutes now. Okay. Just a minute. This is causing a problem. Okay. So we also have, I'll give you some examples. I'll give two more examples before I go. Okay, and take questions from you. There's sensors are extremely important in our, okay, because of water quality, air quality, temperature, any variable that you want to know is sensor. But at the moment their sensors are available, but they are not flexible, they are not disposable, they are not that cheap. Okay, so you would like to make that. We have a huge sensor team at in our this thing trying to work. For example, we have made already gas sensors and breath analyzer. You breathe out, and your sensors get all these things, and from that you can find out what disease you have. Okay, and because of the kind of chemicals that come out with your breath. Okay, so that we are also producing a breath analyzer and microfluidic sensors. That is, channels are very micro, and fluids go in there, so reactions can occur there, and that you can see can be bent to almost 0 degree to 180 degree. Okay, so that is that flexible. I don't have time, so I'll go into. Since you do not know transistors, I did not emphasize transistors, but really thin film transistors is the brain behind this whole technology. I'll take 2 more minutes. Okay. So what is a transistor? Transistor, one of the main function is that it behaves like a switch. Okay, you can switch on and switch off. On your laptop, every pixel, okay, is or even on your mobile is bright because this TFT knows when to switch on which pixel and switch off, and that is why it looks bright. okay, and it is being scanned. So, and if it is flexible, then it can be, displays can be like this, and it actually uses a transistor here. So, this is the display, okay, but behind this is this transistor. This transistor knows when to put that pixel on and the pixel off, okay. And if you have flexible circuits, you can have many of these circuits in an array. That is one of our major development in the thing, that we have a whole array of circuits which are in plastic and can be made. This is not large scale integration, but large scale integration on a very large area, okay. This is in fact okay, and they are, so we have already made, okay, very good transistors with a new material, it's a recent material called indium green. This is not organic, but this is an inorganic material, but you can actually make transistors on plastic, all right. We also print some of these are large scale, we will print with inkjet some of these transistors, all right. So, let me try and summarize. I will give you a few examples, but let me try and summarize what are the challenges which you take home, okay, because this technology has not yet hit the market, okay, and what are the challenges. I will just go through the take home messages in terms of challenges, and that is all low temperature processing, okay, because you are dealing with paper, plastic and textile. What needs to be done? People have made actually glass flexible. Corning has produced glass which is extremely flexible. In fact, you can do roll to roll printing on them, okay, but you have to take extreme care, okay. Just as Corning has come with the Gorilla Glass on your mobile, okay, which is tough, but they have also made it like flexible, all right. So, this is, or even stainless steel, okay, can be made, okay. So, challenge 2, that when you bend and stretch, so I am saying I give you a rosy picture of everything can be done, but there are challenges, and that is why such a big team and the center were working, okay. It is not so rosy, okay, if you see the challenges, but when challenges is there in a technology, that is our duty to overcome them, okay. So, when you bend or stretch, the properties should not change, okay, and that is not easy to okay. So, there are so that it actually you can wear them and wash them and does not change, okay. T-shirt. Challenge 3, these are extremely, since it is being done at low temperature, they are extremely sensitive to the environment and oxygen, and hence each of these devices, actually many of these devices, not all these devices, have to be sealed properly such that water and oxygen does not kill them. That is one of the biggest challenges for this technology, all right. So, this is encapsulation and degradation, oxygen, moisture, ingress. You can see that there are, so that people are trying to think of new molecules which actually help do that, okay. And of course, it is large area, and this is already I have told you about. So, these are the 4 challenges. Our life today is, I said a revolution, I said revolution because this is going to, silicon electronics will be at their place, but this is going to invade us in every area, okay, in our drawing room, to our transport. So, wherever we are, there will be large area electronics which will, we call it actually electronics for everybody and everywhere, kahin bhi, kabhi bhi, okay. That is the kind of electronics, the plastic electronics makes that possible, okay. Otherwise, some of the electronics are extremely costly and we cannot afford them. But in Indian context, this makes immense sense to have it get delivered, okay. So, this is the dream of our area. There are 2 dreams of this area which will never reach soon, will not never reach, will not reach soon, we know, but we work towards that, okay. That is having a computer which will be like a pen, that is a silver pen, okay. If I do this, sorry, what happened? Okay, so you carry a pen and then, okay, your computer is not like a laptop, but is like that, right. The other challenge is a banknote, okay. So, we had recently have new notes, but our notes, by the time we had these notes, there are fake notes also. Even these are new notes, okay. So, a big challenge all over the world is these notes should have electronic security such that it is difficult to crack, Okay, but people are working, but it's not near. It's another 10 years or so. Okay, so I'll thank. But before that, let's go to the lab a little bit for 2 minutes. Okay, let's look at our lab, which is, I cannot take all of you, so, and hence I'll take 2 minutes to get into our clean room. All the lab work that we do is in a clean room. Now she's getting into the clean room. Let's get in the clean room with her, right? So what is a clean room? We have millions of dust particles per cubic meter here. In a clean room, it will be like 1,000 particles per meter cube. Okay, and hence I can't go in an open head. Now you are seeing some of the vacuum equipments. Okay, I told you vacuum and solution processing. You are now seeing vacuum equipments on the one side. They're all computer controlled. For example, he's going to show you a etching being done. Okay, a plasma etch. This is a plasma inside the vacuum, which is etching a particular layer. Okay, in a vacuum. It's a plasma etcher. So now he's showing you. So we have lots of this vacuum equipment on one side. Okay, so this is for sintering with the photons. Okay, with drying with photons. And now for making very fine patterns in conventional electronics, we have lithography, photolithography. So we do photolithography in a yellow room, and so patterns are getting defined now. The below pattern, and now he is going and like a photography, developing it in a wet lab. Okay, so okay, now you have seen this printer already. Okay, we have many such printers, but this is the screen printer, the automated screen printer inside. Okay, so now this is come to solution processing, not vacuum. We have come to solution processing now. Okay, and so okay, so these are this is another kind of printing of big layers that can be printed. This is inkjet printing. Oh no, this is the slot. Okay, so Pixdro, yeah. Okay, so these are printers, and of course the control panels which let you do vacuum. So this is 1/3 of our clean room that we have. We have clean room in 2 buildings. Okay. This is 1/3 in which I showed you the clean room having vacuum equipment, then photolithography equipment, and so these are the rows to make the OPV, organic solar cell, a row of glob boxes, such that your device, when it is getting made, does not see oxygen or moisture. So we have a whole row of them, and inside that we process that to make it. All right. So I have shown you 4 or 5 examples. I have exceeded my time by a few minutes, but if you permit, I can take a few questions, or later after that. Okay, few questions we can have, because we have had a long time me speaking. I would like to see 1 or 2 things that is on top of your mind, and obviously I have shown you some applications. One of my aim was to make you think what would be an application that you would like to have. People still are looking for applications which will be useful. So if you can think of an application and I like it, then we'll work with. All right, we'll work with you. All right. So think of an application which would be really useful to you, and you would dream that, yeah, can I do this? Okay, and you can freely tell us it is possible or may not be possible. But at the moment, I'll take 1 or 2 questions quickly, since they have come all the way. At least some questions. Students must ask questions, right? Sorry? Oh, yeah, yes. The sensors, yeah. That is one of the, yes. Yeah. So, sure, there are many applications, yes. Any other question? One thing that I wanted to tell you as students, okay? Yes. Okay, that's a very good question. Okay, that's except that we use very little. But since we know there is going to be, because silver and gold, why do we use it? Because it will not get affected by, when exposed by climate. So because of that, my chemists have done copper also. Right? So we are replacing now gold and silver by copper, except that copper requires heating still. It is still not at a time. So all over the world, people are trying to use less expensive metal, all right? But the amount of metal used is very little, so that is still, but yes, you would still like to come down. That's a very good question. All right. Yes? Well, we can embed even chips or plastic chips there. Yes. Okay. Now we can even swallow it. Yeah, yeah. You can put it in your brain and you will not think. It will make you think. Right? And such experiments are going on, right? With monkeys already. Monkeys can be completely controlled by putting a chip in their brain, right? The last message that I will give, two good questions, is that you will see this effort in which I showed you so many people, 120 people, 12, 13, okay? And these are completely different backgrounds. The chemists, physicists, electrical engineers, we have even people who design, okay? From art, okay, architecture background. So when you choose your career, and if I want to into an exciting field, there is nothing like any discipline which you like and you are good at, okay, can lead to technology. Technology doesn't know disciplinary boundary. If I only do computer science, okay, and that is my only aim, that is not. Anything that you do, if you do it well, exciting, you can be a part of an exciting technology. Okay. With that, I'll thank our whole Flexi team to make this demonstration and lecture possible. All right. Thank you. Go ahead.
Thank you, Professor Mahapatra, for this. Thank you, Professor Mahapatra, for this engaging lecture. And now I would like to call upon the stage Professor Subramaniam Ganesh, the Dean of Research and Development here at IIT Kanpur, for proposing the vote of thanks.
It's a very pleasant job for me to thank or propose the vote of thanks, especially when the function ends so beautifully. I'm sure all of you enjoyed really well. And my contribution to this event is to request Professor Siddharth Panda that this particular day your center could possibly organize an event to showcase the strength of flexible electronics. There it ended, and he took over. And thanks to the Flexi Electronics team and to all the faculty and participants there. We also have these stall or demo stalls outside. You would get to know about it when you exit the hall just after the vote of thanks. And I would like to really appreciate and thank Professor Mahapatra for the fantastic talk. And all of you, I request to join a big hand in saying thank you. And I also like to thank our director, because he was traveling to Lucknow, and there are a couple of visitors, and still he could come and inaugurate this event and state for the lecture. And a big thank you to all the school children. I mean, who have been here in this hot sun, and you have traveled all the way. And I thank you all, and the teachers who accompanied you, and the school principal who allowed you to come for the event. And big thank you for all of you as well. And our colleagues from the campus, thank you for being here at this event. And I also would like to thank the team members from the Dean R&D division, especially Deepak and his members, who really put in a lot of effort to organize, right from coordinating with the schools to the security and so on. And without such help, I don't think we'll be able to arrange, even if the event is not that elaborate, still it requires a lot of effort. So thank to all of them. And I guess we have now the demo session that is arranged. If you exit the hall on the back side, there are stalls, and there are demo pieces where you can interact with the team from the Flexi Electronics, and you can ask the questions and understand what exactly each of the product mean and what could be the potential and so on. That's a real opportunity. And during that time, we would also hand out a small pack of refreshment. My request is, when you open it, whatever the packing material, there are dustbins, please drop that in the dustbin. Don't throw it anywhere. It may not look good when you leave, right? So that's my request. And I also request all of you to form a queue and then exit via this two exits that you see at the back, right? With that, again, I thank all of you, and I formally close the first part of this event. The second part is the demo, and I again invite you all for the demo demonstrations. Thank you.